According to leading minds across industries, artificial intelligence, machine learning, generative AI, and big data will be the next industrialization catalyst. How might this be relevant today for your company? This white paper by Dr. Michael Treasure provides a window into machine learning applicability in the trucking industry.
This is a case study on the power of data through machine learning in the commercial trucking industry. Specifically, we will be exploring engine conditions. I did this study for at least 3 reasons. One, to satisfy IBM Advanced Data Science Specialization Capstone course requirements. Two, at Timac Technologies, a company I founded and which I now provide consulting services for, Timac wants to maximize the value it brings to carriers operating in its Timac Long Distance Load Interchange Marketplace, TLDLIM, helping carriers to predict manufacturers' engine performance and select routes under loaded conditions and dispatching select trucks on specific routes accordingly is very useful for the reliability of its TLDLIM. Approximately 98% of the trucking industry is made up of fleets of 50 trucks or less. On their own, the carriers of these fleets of trucks do not have resources to invest in high technology such as machine learning. However, taken together, they are the largest enterprise in the trucking industry. The data they provide, when analyzed, can be very rich for helping develop ML models to the benefit of the industry. Let us be more granular in defining the use case. Underpinning Timac Long Distance Load Interchange Marketplace is an IoT platform that streams live data from trucks into Timac's cloud services. One of the IoT devices used in the platform is an electronic login device, ELD, that is a government mandatory requirement in commercial trucks. Timac's IoT platform has 3 devices: the ELD, a camera, and a driver tablet. These 3 devices stream every second more than 1,000 data points, attributes, on each truck, driver, freight, etc. Some of these stream data points are related to the truck engine, drivetrain, transmission, and other connected areas on the truck. The goal of this project is to develop a machine learning model that would use the data from the ELDs of the trucks operating in TLDLIM to predict the performance of commercial truck manufacturers' vehicles by evaluating their general reliability of the truck engines from these manufacturers. Let's define machine learning, ML. On this slide, we can see a plot of 3 attributes: engine RPM, fuel pressure, and engine condition from the actual dataset used in this case study. Human intelligence on its own, without the ability to visualize and decipher the information by some external intelligence system, could not easily find insights into the data. ML is a branch of artificial intelligence, AI, which focuses on the use of data and algorithms to imitate human learning behavior, doing so at scale and improving its accuracy. Insights from the data subsequently drive decision making for business. In my introductory remarks, I mentioned that Timac's IoT platform has 3 devices, namely ELD, camera, and driver tablet. These 3 devices stream every second more than 1,000 data points, that are attributes, on each truck, driver, freight, etc. Imagine multiplying the number of trucks, devices, carriers, drivers, and camera feeds by hundreds, if not millions, dispersed across geography. Then you would begin to see the scale of the requirements to capture, analyze, and provide in real time insights on the vast data sets. Additionally, one must do so with each stakeholder's need in mind and with the security required per user type. This slide provides information on the tool sets used in this project and in general used across the industry for handling ML, AI, and other deep learning algorithms. Some of the tools mentioned on the slide are Apache Spark, PySpark, Python, and Anaconda. This slide shows the architecture TIMAC has in place to handle its requirements in providing its solution. The information and flow provided on the slides gives an end-to-end visual on the enterprise data, technology choices, streaming analytics, etc. For this case study, in developing this model, I followed the lightweight IBM Cloud Garage method for data science process model as depicted on this slide. On this slide, we talk about the actual datasets used in this case study. I did not use actual datasets from TIMAC's platform. Rather, I used two datasets as follows. One, automotive vehicle engine health dataset from Kaggle. Kaggle is a community platform with over 15 million AI and ML learners. It has one of the largest datasets available for use in developing ML and AI models. 2. Synthetic data. Dataset I created that would align with missing data from the automotive vehicle engine health dataset without a negative impact. These slides provide a helicopter view of the combined datasets. There are 19,515 records, 8 attributes that are features, 4 different data types. The dataset consumes more than 1 megabyte of memory usage. The plot shows a distributed set of 6 of the features overlaid to one other feature. The 6 features are engine RPM, lube oil pressure, fuel pressure, coolant pressure, lube oil temperature, and coolant temperature. These are then overlaid against the feature engine condition, and that's what you see on the plot. Here on this slide, I lay out the reasons for the choice of the machine learning technique I adopted for this case study. The chosen ML method was logistics regression. This is a supervised ML algorithm for classification, predicting the probability of a binary outcome. By supervised, I mean you train the ML model based on existing data, then you feed the ML model with new data. The ML model will then give you a set of predicted outputs on the new data, classifying the outputs as belonging to one group or the other. In this case, we want the ML to predict a 1 for good engine condition or a 0 for bad engine condition, based on the feature set we supplied with the values for each feature set. The table you see here is part of the actual prediction of the ML developed with this data set. This slide goes into further details on how the logistics regression function was used, including details on the steps, that is the process model. Remember the lightweight IBM Cloud Garage method of data science process model I mentioned earlier? This slide also shows a table with more details on ML model predictions relative to each row of feature sets as developed in this model. On this slide, I talk about the results and conclusions. We achieved a greater than 65% probability of success for the model. This essentially means that 65% of the time the ML model gets its prediction right on manufacturer's engine condition. Given the evaluation metrics I use, such as mean squared error, mean absolute error, R squared, and other metrics, we have a fair degree of confidence in the ML model's prediction. It should not be difficult then to see how very useful this ML model would be to TIMAC in its TLD-LIM. The image on this slide shows a depiction of how TLD-LIM works. Essentially, 2 trucks on either end of a freight route are paired together to exchange their freight trailers approximately midway on the route. The reliability of each truck, thus manufacturer's engine reliability, is extremely important to ensure that paired trucks do meet up on schedule and are able to complete freight delivery accordingly. The insights Timac may gather from this ML model would help to inform Timac as to which two trucks are best paired together on a particular route to ensure maximum reliability of its TL-DLIM. Additionally, extending the ML model, Timac would be able to proactively provide real-time alerts and recommendations for maintenance or repairs en route for each truck.
The world of trucking has changed. The recent collapse of Convoy has highlighted the need for the trucking industry to take a serious, holistic view of how technology can bring change and resist the need for piecemeal approaches. $875 billion market deserves much more enduring attention, just like any other industry. The Industrial Revolution brought many changes to how we work. The next revolution, we believe, is machine learning and artificial intelligence. What if you could align yourself with the expertise needed to ride this next wave? Based on Dr. Treasure's analysis and the machine learning approach used for this project, we would be willing to engage with any company in any industry to showcase our expertise and practical knowledge.
I am Dr. Michael Treasure, the author of this case study and white paper. Thank you.
I'm Keith Dixon, and I'm responsible for business development and client relationships at Timac Corporation.